So welcome to this Wednesday plenary session. We have two talks before the coffee break. They're 25 minutes talk with 5 minutes question. The first one is from Marie-Cécile from the University of Mohlabeng. She's going to tell us about search for light dark matter and seventh with Hugh SPC students.
Thank you, Leane, for this nice introduction. So yes, today I'm going to talk about direct detection with UG and SPC, searching light dark matter. So we switch a little bit of gear compared to black holes and also stars. So first of all, as we saw already from several talks, there are numerous evidence that the sorry. Yes. So there is a lot of evidence coming from like the galactic rotation curve, a cluster of galaxies, and also a large scale structure that tells us that most of the materials are non-luminous or dark. And this comes from really accurate measurement from a galactic rotation curve, cluster mass determination, the gravitational lensing, and precise measurement of the cosmic microwave background that tells us the energy matter composition of our universe and tells us that 27% is composed of dark matter. But the thing is, we don't have any idea about its composition at the particle level. And from cosmological and astronomical observation demonstrates, in fact, theories propose several candidates, but masses and interaction, as you can see on this figure, span many orders of magnitude. So in my talk, I will talk about light winds, which are a tiny part of this whole spectrum that we have for dark matter, what it could be dark matter. So here I will talk about, as I said, direct detection. The direct detection, in fact, consists to look at the elastic scattering of the nuclei and look for the recoil of the target nucleus. So a very low recoil energy that can be detectable via different channels of detection depending on the target used in your detector. So it can be xenon, germanium, fluorocarbon, argon. And to recap, here is a schematic of possible signals that we can measure in experimental direct detection depending on the technology. So it can be heat or phonons in a crystal. Heat is also responsible of the nucleation process in bubble chambers. We can have also an excitation of the target nucleus, which when this excites release scintillating photons. And we can have directly by a direct ionization of the target atoms. So the detector strategy is to use one of these three or a combination of two of these signals. And today I'm going to talk about the spherical proportional counter, NEWC, so new experiment with sphere gas, and also the SBC detector, which is the scintillating bubble chamber experiment. To be able to compare between all the experiments, in fact, we express our results in terms of cross-section, where all of these limits here is for each experiment that we have. And as you see on this picture, there is two fronts for the nuclear recoil direct detection. In fact, we have this parameter space here of low cross-section, and you need a large detector and a large exposure to be able to screen this parameter space. And you will be talking about this in the next talk by you. And in another front is how can we do to detect the low mass dark matter. And this is here, this parameter space, where we need to have low threshold detector and a low atomic mass target. So as you can see here, all of these limits are approaching very dangerously the neutrino floor here. which will be the main background of the detector when we will be approaching this limit. And it's the solar, supernovae, atmospheric neutrino background predicted by the standard model. And in fact, it's the coherent neutrinos CEvNS that will be the limiting background for all dark matter experiments. And CEvNS can produce nuclear recoil similar to the dark matter, and they cannot be shielded. So these neutrinos, especially in the low mass region, are coming from the sun. And the idea is to take advantage of the movement of the solar system around the galaxy through the eye of dark matter. Then we will observe a relative wave of dark matter coming from the Cygnus constellation. And the experiment sensitive to a direction of those nuclear recoil will see an excess of events coming from this direction. So this will be the signature. So the strategy used by the experiment is in fact to have a directional channel, a directional detector, such as a signal, which will be a talk in the afternoon, or to add the directionality channel to the current technology. And also, we can have dedicated CEvNS calibration using nuclear reactor. So that way, we can see if there is a way to discriminate between the nuclear recoil of a dark matter or by CEvNS. So the main challenge the dark matter community has is that we need to detect a low recoil energy. That means we need low threshold detector. The rate of this dark matter is very low, so we need a large volume detector. And finally, the background is the principal problem for all dark matter experiments. So high purity level is needed, and we need to shield our detector against any background. So let's see now how NUSHI and SBC are handling this. So the NUSHI first is an international collaboration with people from Canada, UK, France, Greece, and US. And the detector consists of, in fact, it's a spherical proportional counter and consists of a metallic vessel filled with a noble gas mixture and with a high voltage transfer. So the active target that we are using is neon or hydrogen mixture to increase our sensitivity to low wind mass region. The readout is typically a single readout channel, but now that we have a bigger sphere, in fact, what is new with news is that we have a multi-anode sensor, the Akinos, which means Earth-Missy in Greek. And we have as well UV laser calibration, so this also is new, to monitor the performance of the detector during a data taking and the physics class. And also it allows us to do special dedicated studies of the response of the detector to single electron levels. So when a particle interacts with one of these atoms of the gas, what happens? We have a primary ionization. The electron drift toward the anode, and at the vicinity, we have an amplification of the signal through something avalanche. And the signal that we have, and we can get, is the current induced by those secondary ions drifting away from the anode. What is very nice with news is that with a 60 centimeter diameter sphere, installed at Laboratoire Souterrain de Monaco in France, in fact, and filled with a mixture of neon and methane for 42 days long run, we get very, very competitive limits in the low mass frame region. So this allows us to go to the next phase, in fact, with a bigger sphere and with a lot of improvement and R&D. So we were going to have, first of all, this Akinos, for the bigger sphere, electro-polished and electroplate inner detector surface, and also a couple of shielding to against all of the environmental. So the first stage was to have this new detector, in fact, was construct. And first operated at Laboratoire Souterrain de Modane in France. So we had this inner part of the surface of the detector electroplated with 500 micrometer of pure copper in collaboration with PNNL. We had the UV laser and RM37 calibration system, the temporary LED plus water shielding, and about 10 days of physics data with pure mapping. And the analysis is ongoing, and the results are expected to be published by the end of the year. And I will encourage you to see the talk by Daniel Delfort at 2 p.m. On the parallel session to hear about these preliminary exciting results. Now this detector has been moved and now it is installed at SNOLAB. So the same detector, as you can see here with the polyethylene shielding and here after the full installation. And we are currently taking data, commissioning data. So the mixture that we will use is neon metal or pure metal. There is still some discussion. And we expect to be sensitive to low wind mass as low as 100 AUV. So what is next for news? In fact, we realized that the dominant background in our detector comes from copper. So in fact, there is a new project, a Cube electroform copper manufacturing experiment, which is an electroform copper facility to be built in SNOLAB directly. And they will take the sphere, so the same size as a snow globe, fully electroformed. And we will use the same snow globe shielding that we have currently. And work are ongoing to produce a mini ECUM that will be, in fact, produced by PNNL in a shallow underground laboratory. And it will be used to define the best condition required for the ECUM, the bigger role. Also, some assays with accelerator mass spectroscopy in collaboration with the University of Ottawa and Carleton are also ongoing. So following this test, we will have a mini detector that can give us also potentially exciting physics in the future. So the strategy for Leane at the moment is to take data with SneoGlobe, currently installed at SNOLAB, with the predicted projection limits here, as you can see. And after that, using the same shielding with a CUMI, fully electroformed copper, with the projecting limit here in blue. And finally, for longer term, dark sphere, which will be a 300 centimeter diameter sphere, fully electroformed as well, where we can see here the projected limit. So we are approaching again dangerously the neutrino floor. And for that, in fact, in use, we want also to study the CEvNS. And for that, we have a surface experiment, MUG3, which will be a unique low background facility at sea level at Queen's University here. And the first step will be, in fact, to mitigate environmental cosmogenic background and study the feasibility to use this sphere to detect CEvNS from nuclear reactor. So you can see here the current design with the compact shield and mirror beetle that will fit a 60 centimeter diameter sphere. In fact, the assembly recently started at Queen's University, as you can see here on the picture, very nice picture. And if some of you are interested to visit the lab and see the installation, Guillaume can be offered to propose a tour of his lab. Now, a new idea that I'm currently working on is there a possibility to add the directionality channel directly with MUG? And the fact that we use Aquinos with 11 anodes, in fact, we can recover the directionality where the particle is coming from. So here, for example, you can see some particles are coming from the left and the right. And if we are able to, if we lower the gas pressure, we will see the track of the particle and then reconstruct the path of this particle. So currently, work is ongoing at University of Alberta. The setup is almost operational, and we are investigating the electronic because the electronic will be needed for all of these 11 anodes. So now let's switch to superheated liquid with the SVC experiment. So the SVC experiment is also a collaboration with people from Canada, US, and Mexico. And the detector reduces 10 kilograms total of liquid argon with xenon, which acts as a wavelength shifter. And the detector consists of a superheated liquid within a pressure control vessel cooled at 160 Kelvin. And the readout is piezoelectric sensor to see the amplitude of bubble nucleation, cameras to track the position of this bubble, and also, since it scintillates as well, silicon photomultiplier to detect the light. So superheated liquids are megastable. So that means the condition and the pressure at which they are is not supposed to be liquid. It's supposed to be gas. So that means if a particle deposits enough energy in the liquid, it will create a phase transition between liquid phase and gas phase. And those conditions of pressure and temperature is exactly the energy threshold. So in fact, here I put is considering in fact as the energy threshold surface energy plus the latent heat. So that means bubble chamber are threshold detector. And this threshold detector is the size energy threshold that we have the heat spike model. So since it's an energy threshold, we don't have any information about the energy that I will talk about later. But why using bubble chamber? We are using bubble chamber because they have an impressive background rejection. So first of all, we can do acoustic alpha discrimination between a nuclear neutral and an alpha event. We can also detect multi-neutron scattering. And also they have insensitivity to gamma interaction. So for example, here from a Piro experiment, we have also fluorocarbon. And here is the probability of nucleate a bubble for gamma interaction as a function of the threshold. So that means here we have about 10 to the minus 7 around 2 keV deposition. So that means we can really be insensitive around the keV level. But again, we don't have any information about the energy. And this is where SVC is coming from. It's a mixture of technology, the bubble chamber by Piro, and the scintillation. So we combine this gamma insensitivity, but also we have this event by event energy resolution. And what is again, we go even further in this electron-neutral discrimination is because if we are going back to the past, Blazars finds no bubble in pure xenon, even at 1 keV threshold with a gamma source. And it's only when he added some ethylene in it that he could see those gammas nucleation. And later on, in fact, another group found for the first time tracks seen in pure argon, but only at extremely low threshold, around 10 eV. So the scintillation process suppresses the bubble nucleation. And this has been verified experimentally. So with a 30-gram xenon bubble chamber, where you can see here the experimental setup, where we were able to see at the same time the acoustic signal and the scintillation signal from the bubble here that we were able to track with the camera. And this has been published in PRL, and new data has been collected after the publication, where we were able to go to size threshold as low as 0.5 keV, where we have evidence of nuclear recoil from a neutron source below 5 keV. And when we put a source of gamma, we didn't see any bubbles at any threshold. So as you can see here, we have really zero bubble compared to fluorocarbon used by people, where we see that the gamma and sensitivity start to increase. So the scintillation suppresses the bubble nucleation. So SBC is very a good detector to low threshold. The physics program is to build two detectors, one for low bit mass installed at Mohlabeng, and also precision study of reactor CEvNS interaction for argon and xenon. So at the moment, we have here the installation is about to be complete. A few silica vessels and bellows, for example, the castle, copper silicon holder, and a piezo transducer. And also we have here all the stainless steel pressure vessel and vacuum jacket constructed, where you can see also quite a regular fit to other system and piston. And here as well, Queen's University, there is also a measure group for SBC, where if you are interested to visit the lab as well, can we say that we can visit also the lab. So the status is to have a SPC at terminal to demonstrate the scalability of this detector, measure the global nucleation probability for gamma and sensitivity, and determine the nuclear recoil that we can achieve. So another one will be at Mohlabeng for low weak mass. The space is already allocated in Mohlabeng. And finally, the same detector from Mohlabeng will be also installed for following the calibration program, will be also installed at the site for the reactor material. Another project that I am working on at the moment is again the directionality with the bubble chamber. And by doing some investigation with molecular dynamics, there is some hint that in the bubble root formation in superheated liquids, there is a dependence of the particle direction, but it's only at a nanosecond time scale. So here you can see, for example, if particle is coming from the left or the right, at the first instant of the bubble, we see a track. But after a few nanoseconds again, we lose completely this information. We can see even better here, where we have the radius of the bubble as a function of time, where at the first instant, from different direction, we can see a directional dependence. So I'm currently working with my group to try to see if we can develop fast camera, new acoustic sensor to reach those extreme scales. At the same time, by working with molecular dynamics simulation, we want to understand also the bubble group and nucleation efficiency. Because the nucleation efficiency is really something really important to interpret the dark matter results. And it is well known that the science model that I was talking about earlier doesn't reproduce the response that we have in the detector. It underestimates what we see. And this has been seen by previous Picasso, Cook bubble chamber, Simple, Pico now, and also SBC. So here you can see the bubble nucleation efficiency, where we have the energy threshold here, and here are the data. So we have discrepancy. And also recently, by doing dedicated analysis, we also find that with Pico 60, we have also this discrepancy. So at the moment, we are using a parametric fit on the neutron calibration data, but there is really a need to improve the theory of the bubble formation and also bubble in superheated liquids for the future. So in summary, I would just say that it's a very exciting era in particle physics at the moment for potential discovery. Of course, we have always new challenge to overpass for the future direct detection. So high purification is needed, background understanding as well, and also finding new ways to go beyond this neutrino flow. So thank you very much for your attention.
Thank you very much, Marie-Cécile. And now the questions from the audience.
A simple question. Is there any bit of explanation why simulation prevents nucleation, which is in a way strange?
Probably it does matter with how the energy is split between the sensation and the nucleation, maybe. Or in fact, it's something that we are also investigating.
So you talked about two potential directions. How do you do it? Is it to scale that as well?
Yeah, it's not so easy. In fact, it's not so easy. So at the moment, what we are doing is just verify that it's feasible at large scale. Then, if really we want to use this technology for bigger detector, it will be a very big project of engineering, and we will need a lot of manpower to see how we can detect the technology. Yeah, yes, this is yeah. Yes, yeah.
Yes.
So I'm a little curious about the principle of directional detection with this spherical geometry. Maybe we can talk offline, but generally when you have a field that is a spherical geometry, you have a strong focusing effect. And so are you talking about measuring the actual direction of each track? Because they will be heavily distorted in this geometry.
Yes, it's true that it's true again when we will decrease, because at the moment it's just a point lag, like a point lag. But when we will decrease the pressure, we will see actually a track. But it's true that I agree that the track will be probably following the electric field line. So we will not have a real track.
And then another thing is that in the region where you're getting the avalanche at the end, there's a lot of diffusion. And so
it's true as well. Yes.
So if we can talk about it.
Yes, I will be happy. Thank you very much for your question and comments.
Any other questions?
You want to point out who candidates want part of that line versus your
Did you plan any meeting point or did you just mention?
Yes, I'm just mentioning now, and then maybe I can
Yes.
send the emails.
Or guys, so probably if you want to visit the labs, talk to Marie-Cécile, the labs are in Sterling Hall.
And maybe you can contact me, or yes, I can send an email via the TeVPA.
Oh, okay.
Yes.
Yeah, maybe a short question as well, if you would set something. So these technologies looking for nuclear goals at the hundreds of the EV, very low energy. It's very challenging to calibrate with these nuclear goals.
Yes.
Can you just comment on the difference between proportional counters and system double chambers? What are the ideas and strategies and work that's been done to understand the microphysics of
In fact, to understand, we need to show the limits of the detectors to very, very special. We will need to have a new source of calibration at the energy. Because typically, what we have at the moment in the aquatic community is that we see excess of energy as very low excess of pivots at these very low energies. So yes, they will give us new ways to understand this energy measurement.
Thank you. Let's thank again Marie-Cécile.
I can get.
That is really.
Is the mic from the for the
Whatever it is.
Sure. Back.
The next slide is from Hugh Lippincott.
Okay, so I will talk about direct detection at TV scales. So this is a more recent version of the dark matter forever space plots. This plot is terrifying to me as an experimentalist. So it was sort of nice to come to a conference that really nails down what I'm going to talk about at this conference. So TeVPA, which I thought meant TeV particle astrophysics. But for this particular talk, we're really going to be talking sort of GeV to almost PeV range, which really is sort of the classic wind thermal dark matter forever space. Okay. So thankfully, Marie-Cécile is going to allow me to get through this talk in time because she covered all this already. But for direct detection of dark matter, what we're doing is we're filling a detector with some target material, and we're waiting for a dark matter particle to bend into that target material, detect the recoil. And kinematics is sort of a key element of these experiments because they drive the energy scales that you're looking for. Because it's just elastic scattering of billiard balls. And so you can, in your first year mechanics class, write down, given the speed of the dark matter in our galactic halo, the size of the target, the mass of the dark matter, what you're expecting to see. And what you're expecting to see is sort of order KeV scale recoils. That's sort of nice. Because it turned out that we thought we knew how to build detectors that could see KeV scale recoils. So there was this nice confluence of technology and sort of target science that says, hey, we can look for GeV to TeV scale particles by building detectors that can see these KeV scale recoils. And that's this completely kinematically driven. A similar thing is now happening at the low thresholds, as Marie-Cécile is referring to, and that new technological developments are coupling to theory to open up new parameter space. But again, I'm not going to cover that too much here. Okay, so we sit and we wait for dark matter to bang into our Plenary. It's a very, very rare process, right? If it happens at all. So the current best limits are at 10 to the minus 47 square centimeters, which is an extremely small number. It's something like 10 million light years of lead. If you were going to shoot a dark matter particle through lead to have an interaction, that's insane. Luckily, and the reason why this actually might work is because there are a lot of particles actually flying around. So as we sit here, there's many dark matter particles flying through us. So you do actually have some chance that you might see something in the detector, but of course it's only something like a few counts per year. So what I've plotted here is the rate in counts per ton of target per year for 10 to the minus 47 square centimeters, which is about where the current best limits are in the field. And there's a couple of targets there. The only thing I really just want to point on this slide is A, the y-axis goes up to 2. So, 2 counts per ton per year. There is an exponentially falling spectrum. So you would like to be at low energies if you could. And there are some dependencies on the target. In this case, this is for a spin-independent interaction. So heavier targets turn out to be better because of the coherence. So xenon has a slightly higher rate than germanium, has a slightly higher rate than argon going down. And that's, again, sort of a state about coherence of the interaction. So this all sounds maybe plausible. You could look for 2 counts in a detector per year. Problem, of course, is backgrounds. And Marie-Cécile also referred to this. The issue with these experiments is that if you have a very sensitive detector on the surface, it's going to go off 10 to the 12 times per ton per year, and you're looking for these 2 counts. So understanding backgrounds is key. So the goal of these experiments is to maximize the dark matter that basically means go big while controlling backgrounds. Okay, here's the classic dark matter plot. Marie-Cécile also showed this type of plot. On the y-axis is this interaction strength. On the x-axis is mass. And generally what happens is we draw exclusion lines that look like recliners. And that is also sort of a very simple sort of follow through of what the interactions look like. So at low mass, things shoot up, our sensitivity is in the hands. They shoot up at low mass because of the detector threshold. So the kinematics of the scattering again say that for a light dark matter particle, it is hard to give a big kick to a heavy target nucleus. And so at some point, your detector, which is a real detector, has a finite energy threshold. You can no longer see the interactions at lower mass because of kinematics. So you basically just have no sensitivity on the low side. At the high side, what's happening is we have the density of dark matter from galactic measurements. So we know the density, but we don't know the mass. But therefore, the heavier the dark matter particle is, the fewer particles there are. So there's just fewer in the detector. So this just goes up linearly forever. And it's sometimes a misconception because we only ever draw our lines to some mass, but it actually keeps going as far as you want to draw it. Here I've cut it off at 100 TeV, which is a sort of theoretical bound from unitarity, but you could go farther if you wanted to. As Marie-Cécile said, if you want to go to lower mass, you need to work on the threshold. If you want to work at higher mass, you need more exposure, which basically means size. So size while reducing backgrounds. And then eventually we'll be limited by the neutrino fog, which again I'll come back to later. Okay. So what are we looking for? I'm not going to dwell on this because of this venue. I don't think I need to dwell on this. But we're trying to measure, a wide variety of parameter states where there are lots of existing models. Direct detection has been very successful over the last 2 decades, but the region that we are probing now continues to be very, very well motivated. And both spin independent and spin dependent, which are 2 parameterizations interaction. Again, I'm not going to dwell on this in this audience. Okay, so direct detection at a TeVPA. What are we doing? We need more sensitivity. We want to scale up the target. So we're now into the multi-ton scales, and I'll talk about that in a bit, but we need to reduce the backgrounds. So I think there's some 3 main legs on which you stand to do this. The first is radio purity. To build a detector, you need to use real materials, steel, glass, etc. Those things are radioactive. So experimentalists go to extreme lengths to make sure that the detector is as clean as possible. On the top right are 2 germanium cameras in the underground laboratory in South Dakota, where every single component of the experiment I worked on was screened to make sure it was low background. Second thing you do is you try to shield your experiment, in particular self-shielding. So down here is a sort of cartoon of what this looks like. Again, you build your detector to something real. If you can make the bulk target sort of pseudo large, then the edges of that target, which is producing radioactivity, can range out on the edges of your experiments, leaving the center to be clean. And this gets bigger and bigger you are, right? So for a small detector, the center that's clean is small, but for a larger detector, now you have more volume and no background. And the last key to these experiments is discrimination. Again, Leane and Marie-Cécile's explanation of this. In particular, you want to discriminate nuclear recoils, where in our case, we're looking for a dark matter particle banging into the nucleus, giving us a nuclear recoil or an NR, that's our signal. Most backgrounds from gammas, from betas produce electron recoils with the interaction with an atomic electron, and that's the thing that goes with the detector. You can tell these things apart in the distance. Low thresholds in this mass range are important because of that exponential decay, but not as vital as they are for the very, very low mass detectors I mentioned. And we would like to explore as many interactions as possible because we do not know what we're looking for. So we want to cover as much space as we can. So that falls for things like different targets, sensitivity to various types of interactions. All right, so at the TeV scale, there's 2 main sort of classes of detector I want to talk about. There's the large liquid noble detectors, which includes liquid xenon and liquid argon, and then there's the bubble chambers, which uses Pico as the example. The things that these detectors all share are that they're liquids. So in some sense, that means they're scalable. You have a bucket of liquid and you want more, you buy a big bucket, you put more liquid into it. That's effectively what we're doing with a lot of details suppressed. They all have excellent 3D position reconstruction. So the TPCs, which we'll talk about, in Pico, you take pictures so you can pinpoint the location of the event. That allows you to reject the surfaces and do this visualization. And they all have really good ERM representation. So again, all 3 of these techniques, or 2 of these techniques, depending on how you're counting, have these elements in common. Okay, so Pico I'll talk about first. I won't go into the details because Marie-Cécile just did it for me. I will just say that the technology is super cool, right? You're completely blind to the biggest backgrounds that other experiments have to deal with. They just don't even make bubbles in the first place. And that's an exquisite level of rejection. The y-axis here is 10 to the minus 10 here, where it's like the probability of an electron recoil to make an event in your detector. The acoustics of also super cool. And just to give this a longer version, you can play the sound that the bubble makes, and that tells you something about what the interaction was. And most of the time for Pico, you're using a fluorine target with about a 3 kV threshold, just right in the sweet spot of what it is. Pico has a whole family of chambers that are growing in size. This will be a theme. Pico 60 has the world's most sensitive spin-dependent proton result. That is from the Pico 60. A sort of different design is being commissioned now, Pico 40 out there, designs for Pico 500, the next scale up going on. There are several new results on different types of interactions, and okay, noble liquids. Again, liquid xenon, liquid argon being the big ones. Similar story, right? A slow scale up or a fast scale up of scales. And we're now into this era of experiments in multi-ton scale. So one slide on how these things work. For the TPCs, again, this was being a big bucket of liquid. In this case, you will also apply an electric field, and you put light sensors at top and bottom. And what happens is radiation will come in, bang into a xenon nucleus or a xenon electron, and cause recoil. You get a very quick flash of light. This is the scintillation that Marie-Cécile is referring to. We collect that and call it an S1. And then you also free electrons, which drift through the electric field and are collected at the top in a sort of an amplification phase. And that's called S2. And so you get your position reconstruction by taking the Z from the drift time, the hit pattern in the top gives you XY, and then the ratio of charge to light, which is effectively the ratio of S1 to S2, gives you particle ID, whether it's an ER or an N. Okay, so liquid argon first. There are two main sort of experiments or collaborations working. There's dark side, which does exactly what I just talked about. There's deep, which does this in single phase. So that is just one bucket of liquid. And the reason that this works in argon is that you have excellent pulse shape discrimination between, again, ER and NR just from the timing. So argon has this really nice property where you can tell apart the two types of events from the way the scintillation light is produced. Dark side 50 was an experiment that ran in the late 2010s. They used 150 kilograms of underground argon, which is a nice innovation. So, quick sidetrack, argon that you get naturally on the surface has cosmogenically activated argon-9. It's a radioactive decay. It gives you something like a becquerel per kilogram of activity. If you remember back to the numbers we were talking about, becquerel per kilogram and a ton per year, you're talking about a lot of events that you want to get rid of. So underground argon is suppressed, and Darcy was able to discover, to develop this technique to use this argon. And they recently presented results 2 weeks ago. Slides there. Deep 3600 is in Snow Lab. There's a talk today from Simon Weil, I believe, at 2:20. I apologize for messing up. World-leading results in very high mass dark matter, and the demonstration of this PSD in really exquisite control. They did have some backgrounds from CEvNS, which calls back to the 3D position reconstruction. So one of the downfalls of a single phase or problems to solve in single phase is you don't have as good 3D. So it was harder to reject these events in the neck. They had put in some upgrades over the last year to address this problem, and they're hoping to restart at the end of this year. Okay. These experiments or collaborations have all merged to form the next generation version of the liquid argon technique. There's a planned dark side 20K detector LNBS. And here we're already talking about 700 tons of argon. So really, a massive detector. 20 tons of it is the fiducial volume of the underground. So there's a significant R&D with cryogenics, CEvNS readout, neutron vetoes, which is undergoing. And they've actually started installation of the cryostat in a hall south of Italy. And I recommend you see talks on that scales. Okay, switching to the xenon detectors, there's 3 of them. Panda X is located in China. It's about 4 tons of active liquid xenon. They were able to get a commissioning run last year. I actually set world's best limits last summer. They had, and the next 3 slides, I'm going to be giving this number of counts per kV per ton per year. If you recall, maybe 10, 20 years ago, the sort of unit of currency was the DRU, which is counts per kV per kilogram per day. And now we're talking about counts per ton per kV per year, which is 10 to the 5, 10 to the 6 orders of magnitude of improvement in background level. So they had 50 of these in the ER counts, but they had some residual contamination from a tritium background that is now currently being addressed by a purification campaign, and they'll hope to start again soon if they have another. The xenon endpoint experiment is 6 tons of xenon located in Italy. A couple of features of their detector is liquid purification. To turn this huge mass of xenon around takes a lot of work. If you can do it in liquid, it's much, much easier than if you can do it in gas. They also have a radon distillation system. So I haven't dwelled on any particular details of backgrounds, but like argon 39 was a problem for the argon experiments. Radon is a big problem for the xenon experiments. Radon is a noble gas. It's at the end of the decay chain of many materials that you find in sort of radioactive materials that you find in everyday stuff. And it can emanate out of the material into your bulk liquid. So radon is the biggest background for these experiments because it mixes into the whole detector. There's a beta decay in the chain that is on its own, and so you get a naked ER detector. So they have a column to reduce their radon rates, which is working quite well. Their cathode voltage, which is one of the grids that they put to drift for the electrons, is not working quite as they had hoped, but they are still able to operate. So they took science data from July to November of last year, and they presented their first results at the IDM conference 2 weeks ago. And one of the really nice things about this detector, 16 counts per ton per kV per year, again, which is just an exquisitely low background. So what are the results? This is not the classic WIMP space. This is in the ER band. So many of you may remember 2 years ago, their predecessor experiment, Xenon 1 ton, in their last run, presented what looked to be a potential excess of background right here at the lowest end, at around 3 keV. This could be caused by some radioactive contamination, but it could also have been evidence for some new physics process. Unfortunately, Xenon Edison is not able to come along. This is the result. And what you can see is that they've lowered their backgrounds tremendously, but also there's no sign of this excess of abnormal issues. So there were a lot of papers following this excess. Well done, everybody. But it's gone now. So they have new limits on some of the types of physics that explain excess. And when you look at new boards talking about EM, and they have to. All right, and then I'll talk briefly about LZ, which is the experiment I work on. So 7 tons of xenon active volume, so the largest of these 3 experiments located in South Dakota in the SURF laboratory. I want to highlight the gadolinium liquid single neutron veto. I haven't talked about neutrons very much. Neutrons are a big problem for us because they can mimic what a wedge signal would look like. So you would really like to know exactly how many neutrons you have and where they're going so that you don't mistake a neutron for a WIMP. I think this is key for making the discovery. LZ was filled last fall. Here's sort of a timeline of project approval stage, if you care, to getting things sort of installed and filled. So it was filled last fall. We were able to take a run from about Christmas to Easter, interestingly enough, about 60 days, and the first results were a month ago. Our benefit rates were, again, 25 counts per keV per ton per year. I'm going to advertise Sam Harris's talk tomorrow. I'm also going to steal this thunder a little bit, so I apologize to him. So this is a picture of LZ. All of the xenon TPCs look roughly similar. There's Teflon for light collection. There's an array of TNTs on top and on bottom. And they just look cool, I think. This is people making sure there's no dust on the detector. Dust is a problem and it's radon. So there were huge amounts of clean protocols in place. You can see the people there. And this area is critical for background rejection. This is a picture of the outer detector. This is an acrylic tank made by the same people who make the acrylic tanks on the high hotels in the Middle East with fishes in them and stuff that you can swim in, 1,000 feet up. It was harder to get our tanks, I think. But this is still stimulating the light function. So a quick sidetrack into calibration. Calibrating these experiments is really important. So discrimination I've been hitting as a highlight throughout this talk. What does that actually mean? So here's a plot of S2 or charge in the y-axis versus S1 light on the x-axis. And what I mean is that if you look in the ER band, so where an electron beam below background makes signal, it follows this blue distribution. Whereas if you look in the signal band where WIMP would make an action, it follows the red below. So you can see that there is this separation. But calibrating the separation is just crucially important if you really want to know what you're talking about. So fortunately, we can do that. So in LZ, they're able to inject tritium in the form of tritium methane to have a very high statistics, a sample of low energy electron recoils, much higher statistics than the actual background rate you see in the experiment, the points from the left to the right. That enables us to really finally model how ERs distribute themselves in all of our parameter spaces of interest. We also can directly calibrate what the signal looks like using neutrons, right? So neutrons mimic WIMPs. We can inject neutrons, in this case via a DV generator, and see what the WIMPs look like. This is a feature of all these direct detection experiments that many people outside of the field would be jealous of, that we really know what the signal will look like for this particular signal model. So that allows us to precisely model signal and background the final analysis. All right, so here's the result. Fortunately, there was no discovery. But we do have very sensitive limits on the 60-day run, just to show that the experiment is working well. And I think it's interesting to point out that we are now passing this 10 to the minus 47 square centimeter barrier. And again, I would advertise Sam Ericsson's talk for further details of the analysis and the experiment. All right. So what's next? It's sort of unique, amazing, odd. There are 3 almost identical experiments running at the same time in the world. That's probably not going to persist to the next generation. We recognize this. So the Xenon and their follow-up Darwin Z, we've decided to come together to try to build, the one Xenon experiment to rule them all. And that is now called the XLZD Collaborative Consortium. We had a good meeting, 2 months ago. And there's a white paper that talks about the science. And this instrument will truly be a multi-purpose experiment along the lines of some of the things I've heard about here at TeVPA, actually. So I hope you stay tuned for that. All right. So some sort of final comments. The famous Moore's Law plot, this probably won't be the first time you've seen this in the context of dark matter. The number of transistors doubled every 2 years, factor of 10 every 6.5 years. We've been doing better than that in the WIMP dark matter world. So the sort of faded red line at the top is the same Moore's Law scaling, and you can see we're actually going faster. Rick still made this slide, but it's something like a factor of 10 every 3 years. So we have been making a lot of progress, which is really, I think a testament to the field. So it's, unique that there are 4 multi-ton detectors operating simultaneously, with more on the way. We've been able to demonstrate the technological maturity of all of these techniques, but I think it's important to know that building these detectors is hard, right? This is not easy. Every time we build one, we find something that we would like to fix. So that has to be built into the next design, but I think we're ready for one more push. So here it is just the liquid bubble, sort of a similar version of Moore's Law. You can see sort of the scale here, where you come, I don't know, 4 to 5 orders of magnitude over 15 years-ish, and we're hoping to sort of do one more thing when we get into this neutrino fog. So let me make a few comments about the neutrino fog. Here you see this plot. This is the neutrino fog, and Marie-Cécile alluded to it. What is the neutrino fog? Neutrino fog is where atmospheric and solar neutrinos will make coherent scatters in your detector that look otherwise indistinguishable from WIMP dark matter because they make nuclear recoils, right? So I'm calling it neutrino fog, proposed by Karen O'Hare in this paper and adopted in the SNOMAS paper as a rebranding of the so-called neutrino floor, because it better captures what's actually going on. It's not that you can't make progress in the fog, it just makes it harder because there's a new background. So the way we've tried to parameterize this is using an index 10, which is how fast we can make progress. So an increase in sensitivity by a factor of 10 requires 10 to the n more exposure, right? So I hope that makes some sense. Here's a version of it with some nice pictures. And I think this illustrates the point that we're trying to make, right? These are locations of particular types of neutrino sources, and the color scale is this index 10. So not everywhere is the neutrino fog as bad as it is in other places, right? And the axis up here goes to 2. Obviously, gaining sensitivity like the square root of time is not ideal, but it's better than getting sensitivity like, I don't know, the 10th root of time, which, we'd all be dead. So I think that's a way to talk about neutrinos that is slightly more nuanced about what's actually going on here. You can get into it at some level, you just takes time to watch exposure. Other things you can do on the neutrino fog would be make measurements of the atmospheric neutrino uncertainty, right? So if you really know the background, you get back to that square root scale as opposed to the 1/10 square. So that's one way you can make progress. You can be clever in your use of target. Fluorine-based spin-dependent detector can go much deeper than a xenon-based spin-dependent detector because of the way scaling works. And and that the coherence goes like the number of neutrons squared, whereas the spin goes like just the number of unpaired spin. So you can see that the xenon floor in this coupling is much higher than the fluorine-based floor in this coupling. Directionality, I won't be able to dwell on, but we talked about it the last slide. Directionality is another way you can make progress, where you can actually separate the neutrino background from wind. I think the main issue with these experiments is that, this is one example. They're building right now a meter cube demonstrator, but because of where the current sensitivities are, we need 10,000 of those things to get to, where the current best sensitivities are. You can do a bit better on the spin-dependent case, but it's still talking about massive scalings up from where we are now. So that's a long program, but it'll be needed if you want to make more progress. All right, I have 1 more minute. Dark matter is important. I think everybody here would agree with that. So SNOMAS is this US planning process, long-range planning process. It's been a lot of fun. I'm sure many of you have taken part. Here again is this terrifying SNOMAS version of the usual range of parameter spaces that we're looking at. So I was excited because I thought TeVPA was really going to talk about TeV particles, but of course that's not entirely true. I have something that's yes, we're really talking about, I've seen talks about almost every part of this parameter space, even at this conference. So there we are. What is the strategy in the sort of TeV range? We want to go next generation. We want to delve deep. Ready for some branding? Delve deep. We want to go really into these high priority targets. So WIMP dark matter remains extremely well motivated. We know what we're doing. We're ready to build the next generation experiments. We want to go as deep as we possibly can to explore that parameter space. However, we don't want to be blind to the fact that we really don't know what the dark matter is. So there's an aspect we want to search wide and not rule out or close ourselves off from looking at other regions. So the strategy, hope you buy in, right? Dark matter is important, poses an important problem, really would be revolutionizing to particle physics if it was detected. To maximize that just probability, we want to delve deep, fully explore these high priority targets. So WIMPs, QCD sounds being the other good example, while at the same time developing the techniques and the understanding to be able to look at these other scenarios so that we can maybe delve deep on those in the future. And it's important to know that dark matter crosses boundaries, right? On every frontier in the US framing, neutrinos, accelerators, colliders, is looking for dark matter in some form. And so having that complementarity, a vital theory program is important if you really want to make this discovery. So here's where we are now. Here's where we hope to be. Here's where we hope to be, like detecting as we make progress in all these fronts. And maybe I'll stop there. So direct detection, we're really into the multi-ton era. LZ has great influence, but consortium in dark matter, and there's a lot of interesting talks and science happening. So stay tuned. Thank you.
Thank you very much, Hugh. We have time for questions.
Yeah, if we just asked you the results you showed from Leane and Ton, where the excess disappeared. Is it understood? For example, did they do some tritium mitigation or anything like that? That might point to that.
I think there is still disagreement out there about what was actually going on. They say that it's most likely it was tritium. I think LZ has the sense that it might have been argon-37, which makes it peak right in that range. There are arguments why they don't think that they were seeing argon-37 about distillation and things like that, and the size of necessary air leaks. I think they built a new detector, and so any tritium that was containing the old one, they were able to bake out and purify out. I'm not sure we'll ever really know. They're not going to go back.
Will you be recording and releasing S2 only data to be sensitive to light or dark matter where you don't see a situation like then you're going to hold the ability to spectrum.
Yeah. So I focused on the TV range, but of course we want to do as much science as we can with these experiments. So the question was about S2 only searches, which lets you dispense with the light signal and push the thresholds down to go to lower masses. There's also sort of the Migdal effect, which we're looking for. So for sure, all of these experiments are working on that type of analysis. I think there's a lot to be done there. The thing you pick up when you do that, of course, is it's not actually the rejection, I think, that you lose, it's the position rejection, right? So you end up getting the surfaces back in a way that you don't have in a nice, clean, light charge event. But certainly every experiment has that as something that they're working on, because as you say, you can get new sensitivity. These are huge experiments and very quiet experiments, so it's definitely worth doing that analysis. So yeah, takes more time.
So as you extrapolate up, eventually you hit a flux line where you just don't get enough particles moving through your detector in like a year, and that happens roughly around like the Planck mass, oddly enough. I'm just wondering, at that sort of cross section, you then have to do multi-scatter analyses in your detector. Is LZ looking into this?
I actually don't know the answer to that question, which is somewhat embarrassing. I'm sure someone is looking at it at some level, but it's not at the moment at a top level. Yeah.
That's not.
I hope someone doesn't kill me for saying that. It's not on my radar. There's 150 people in the experiment. Yeah.
So you mentioned the slide for the outside experiment uses 700 tons of diplet carbon, but 120 what happens to the other?
Let's see if I can go back quickly to show the design. It's basically shielded. So let's see. And somebody who's in the dark side may want to correct me if I say something completely wrong. But the cryostat here, I believe, is somewhat developed by CERN for the Dune program. So those are a relative size cryostat that they don't have to be engineered. So that's a nice thing. So they build the TPC in the middle. They fill that with 100 tons of underground argon. And then there's a fiducial volume, that's the 20 tons. But argon is still a really good detector medium. So it scintillates, it can see neutrons, it can veto all kinds of crazy crap, and it can veto and shield from radioactivity in the cryostat. So, to fill this much space in this cryostat requires 700 tons, and so that's what you're going to fill it with. I mean, at some level, it's sort of an engineering, mechanical engineering constraint based on what they're using to run the experiment. I hope I didn't say anything wrong.
That's basically right.
Great.
It's a 700 ton atmosphere.
Yeah, so this is all atmospheric. So I think it's only 100 tons of underground, which is still a lot, but less than 700.
It's 50 tons.
50 tons? Okay, thank you. The numbers moved around in my head. Thanks. Maybe I should sit down. I got to do a piece of coffee break.
No, that'd be great. Okay, thank you very much. Let's thank you again.
The Southwest with Leane, talking about that stuff. Right.
Thanks. All right, thank you very much for the invitation to speak today. It's really a pleasure to be here in person and seeing so many of you here. So today I'm going to tell you all about how we can detect dark matter using different celestial objects. So just as a brief outline of what I'm going to tell you about today, so I'll start with how dark matter can uncaptured in different objects. So just really briefly, how does this work and how does this give us potentially detectable signals? I'll then tell you about some ideal properties of different celestial objects. So why we want to use some more than others in different contexts. In particular, what are the different locations we want to go looking for dark matter signatures on these objects. So I'll focus on two classes of searches today. So I'll start with something called feeding searches. And these, I think, have really gained a lot of traction in the last few years. So I'll try to explain to you why, particularly now, I think these searches are interesting. And I'll talk about a range of different objects. I'll try and review kind of the state of the literature where we're at the moment for different objects. So I'll cover the Earth, I'll cover white dwarfs, neutron stars, and exoplanets. For the second part of the talk, I'll tell you about another class of searches, so particularly looking for standard model products directly. So we'll speak about neutrino searches and gamma ray searches. And of course, this is a really broad topic, as we've already seen at this conference. It's really hard to cover everything. So at the end, I'll just flash it in case you're interested. All some of the great things I just don't have time to mention. All right, so how does this general picture work? Well, we think we have, a visible matter in the halo. We have a galactic halo of dark matter that's much, much larger than the visible content of the galaxy. And throughout this dark matter halo, we have lots of stars and planets just peppered throughout the dark matter halo. And what can happen is dark matter particles can come into contact with any of these stars and planets. And as it comes into contact, it can lose energy, so it can scatter. So the basic assumption is we need dark matter to interact sufficiently with the standard model. But it can lose energy and become gravitationally captured. And over time, more and more of these dark matter particles can build up inside these different celestial objects. And under the assumption you have a dark matter candidate that annihilates, what can happen is these particles can find each other and annihilate into standard model products. And what happens next depends somewhat on what particle physics model you have. So under the assumption that dark matter annihilates to something fairly short-lived, what can happen is these standard model products are just produced inside the celestial object and they're just absorbed. So you can think about dark matter as converting its rest mass energy into energy that can, in the end, actually increase the temperature of different objects. So this is something, for example, which we're looking for in infrared. And I'll tell you about some of the other searches briefly. So what object do we want to do to go looking for these types of, what sort of objects we're going to use to look for these different signatures? So it turns out actually there's lots of not working on microphone, sorry. Yes. I'll just hold this. One second. Is that working? Any better? You can hear me okay at the back? Great, thank you. All right. So it turns out there's lots of different objects that you can use. And actually, I think there is no one perfect detector. So there's not just one object that's the best in every case. So depending on what type of search we're doing, there's different objects that we want to use. So the general sort of features we want to optimize over for these searches are as follows. So first of all, generally want a big object. So if you have a bigger radius, really simply put, or at least a bigger effective capture radius, you can capture more data. And if you capture more data and they're annihilated, you're just going to get a larger annihilation signal. Fairly straightforward. Another feature that we like is for the objects to be fairly dense. So if they're dense, this just means generally we can program weaker interaction cross-sections. Because if an object is really dense, it's just very efficient. Something else is the core temperature of these objects. So if you have a really high core temperature of the object, what can happen is dark matter particles will come into the object, they get a thermal kick, so they get some kinetic energy. And if this kick is too big, effectively what can happen is the dark matter particle will just leave the star upon, and you might not have the signature that you want to have. So we want to optimize over what this temperature is, how dense it is, how big it is, to probe most optimally the dark matter parameter space. But we also have to think about where we put these objects, because really obviously put, the detectability of the signal matters. So it really doesn't matter if I have a huge annihilation signal, but I put the object on the other side of the galaxy, or if I put it in some environment where there just isn't a lot of dark matter. So we want to think about the flux further away for an object, gives us a lot of around square suppression in the flux. And if the object really is small, its luminosity is like the surface area of the object. So even if an object is, giving us lots of this annihilation, but we can't see it because it's too small, we don't get to see it. So we have to think about optimizing all these different features, as well as the background expectation for what environment you put it in. For example, if there's lots of dust, maybe you can't see it if we go into the ones with the wavelengths. And there might be some internal backup as well. For example, if we have nuclear fusion, you might not want to do a heating search. So here are the summary of different locations we've been looking for dark matter signatures from celestial objects. So one of the classic ones really is just the local position. Local position is great. It's close by. 1.5 square can really do it. So local position is the best if you can actually do it. Problem with the local position is we don't have so much dark matter compared to other places we might want to look. Which is why in some cases, if the object really is detectable, we'll be thinking about places like globular clusters. So these are just really big clusters of stars. And these maybe have a lot of dark matter. This is really controversial. We don't know what components they do. But under the assumption that they had a lot of dark matter in them, maybe we could see some dark matter signature. Another obvious one is the galactic center. Lots of dark matter seems probably greater. The velocity is also fairly low potentially, but again, it'll be limited by dust. So best feature, we want high dark matter density, low dark matter velocity, close by if possible, and older environments and things have had time to kind of cool off, and also low dust. We're not going to get all of these, but we want to just optimize everything we can. So as a recap so far, lots of different objects, they have unique temperatures, unique properties, and different ones are going to give us different sensitivity to the cross section. Lots of places we can go looking for them, lots of signatures. So now let me tell you about some of the heating searches that have been done before. So what we're going to use for heating, something preferably that is just not too hot. So most planets are fine, generally just not things that have nuclear fusion. At least the local position, something like the sun is not so good. In terms of the detectability, where do you want to look? What instruments can we use? So the coldest stars and planets that exist are around 50 Kelvin. So generally in the spectrum, we're looking fairly deep into the infrared if we wanted to measure without any dark matter heating, for example, just the temperature of the planet. And depending on the properties of the object, it's possible that dark matter can push you up into the UV, X-ray, optical. But depending on where we try and do this search, we can't, if you go into these really short wavelengths or very far away, because you have lots of dust. So something called dust extinction just can reduce the strength of the signal. So I think these suite of telescopes that we have now are really the main reason why these heating searches have become really interesting in the last few years. So as an example, or I think these are really the best ones that we have. So the Hubble Space Telescope, you've heard of and probably think about this for its pretty pictures. So it's mostly the optical, but it turns out we can actually use this to track it for dark matter. It's been done before. So I'll show you that briefly. The JWST is really just absolute powerhouse. It is the best. Personally, really big fan of the images from that. But the great thing about JWST is that you can see really far into the infrared. So we're going to be able to look at really cold objects, which means that we can really push down our sensitivity for dark matter heating. The Rubin telescope, which hopefully will have first light in the next year or so, also can see these particular signatures. They're not as sensitive as far into the infrared, but they're near infrared and optical. And also the Roman telescope, I think, is going to be really promising. So we're also looking at a launch of, I think this might have been pushed recently back to about 2027, but at least like roughly the next 5 years, we should be able to use that. So the point really is here, we just launched Webb. We have almost these other two. Now is a great time to be thinking about how maybe we can use these to find dark matter, and they should be sensitive to the scenarios we're interested in. So now we're going to go through the searches that we've done before, how they work, and what they mean for dark matter. So the first and most obvious one is the Earth. We live on the Earth, of course. Why not go looking for dark matter inside the Earth? So this has been done in a number of papers, and each time now I'm going to show you an object. I will try to show you semi-comprehensive list of the papers that have been done on this topic. So that's going to have implications for the masses that we can have. And the amazing thing about the Earth, and I really love this, is that we've tried to study the Earth in a lot of detail in the past. So geologists have done something like 20,000 boreholes through the Earth's crust. So these go down something like 12 kilometers. And we have so much data on actually what we expect from the internal heat flux of the Earth. And this means that really our systematics are quite low compared to trying to point our telescope at something somewhere else. We have a lot of data of something right underneath us. So systematics are low, we have the data now. Proximity is great. The limitation for the Earth is really just that it can't prove as light dark matter masses, and the cross-section reach isn't as good compared to some other things, just because it's not a very big object compared to other things might not do that. So to see what you can really do with the Earth, it's just pointed out in the paper in approximately 2007. Comparing to, say, classic direct detection, this is the underground detectors, some astrophysical constraints at the top, and then some of our surface experiments in shaded red. Remember, this was the status as of 2007, so this picture has changed a fair bit since then. But the Earth can prove fairly large cross sections. The dark matter mass is roughly in this range. So we can have constraints already from the Earth which is great. We should also see this really cool paper by Joe Monte and collaborators, where they also looked at Mars actually too. The point is we can use Earth right now to get some pretty strong constraints. But we're going to want to go to bigger, more dense, more extreme objects to get some benefits of potential benefits. So the next one we want to go to are white dwarfs. So white dwarfs are roughly Earth-sized, but they're much more dense. So their mass is roughly one solar mass packed into something Earth-sized. And if you haven't thought about a white dwarf before, they just come from collapse of main sequence stars, provided the star had a mass less than about 8 to 10 solar masses, and they're supported against gravitation and collapse by electrons and density pressure. So, what do we do with white dwarfs? This is where we can use the Hubble Space Telescope. So, Hubble actually already looked at a global cluster called Messier 4, which is fairly close by, and has measured white dwarfs in it. So, we have the data now. Seems great. What are really the limitations here? So, because white dwarfs are generally very hot, they don't have a very low background temperature. You want a lot of the dark matter flux to heat it up above its background expectation. So that's why they want to go to global clusters, because potentially there's a lot of dark matter there. Again, I emphasize this is not actually really known that this is true, but under the assumption there's lots of dark matter in those globular clusters, this is one of the best objects that you can use. So what are the benefits? They exist in the cores of globular clusters. Other objects don't, they get kicked out. We have the data now, we can probe quite low dark matter masses, and we're going to get better cross-section sensitivity in the Earth. So that was shown more recently in this paper. So this blue line, so I should say the y-axis is the spin independent scattering rate of the standard model of dark matter. The x-axis is the dark matter mass. You can see other constraints in the shaded regions, and what they think they would have for their reach under the assumption of particular type of interaction that's shown at the top, and particular mass in the star. You should be able to get anything above approximately the blue lines. So you see the reach is really good. This search just has a pretty strong caveat that we don't really understand the astrophysical uncertainties of this. Next up, neutron stars. Neutron stars are just the boss of all this. Neutron stars are extreme. So there is a reason this list of papers, which really isn't complete, you might have noticed compared to everything else, is much longer. It's because these are just great cases to go with the dark matter. So neutron stars come from collapsed cores of heavier stars, so we're looking at like 10 to 25 solar masses, and they're supported against gravitational collapse by neutron density pressure and nuclear forces. So they're generally pretty small, like 10 kilometers, but they have a solar mass packed into this tiny planet size, which means they have huge escape velocity, which makes them really great for trying to probe dark. So what data do we have for this? Nothing yet. The hope is that this is something we'll be able to measure with JWST. The limitations of this is that neutron stars are very small, so you need a candidate that's very close by. And we don't yet actually have a candidate neutron star to use. Doesn't mean we won't find one, but so far we don't know. And the exposure times required can be large to see something so small because the luminosity just goes with the surface area of the object. But this in principle is something we could do. And of course, the benefits really are just amazing for neutron stars. So they have the best cross-section sensitivity of all the objects. So if it turns out dark matter has very weak interactions with the standard model, these are the ones that are going to find it using these types of searches. And really the great thing with the neutron stars is that you get a boost in your annihilation rate from something called kinetic heat, which is just that when they come in, they're sped up to relativistic speeds, so they have just a lot of energy, and this is then deposited and we have something on top of just annihilating. And generally this means we can really probe a broad class of models. So this was pointed out, in particular, the sensitivity of JWST in this super awesome paper from 2017. And I think this paper was really responsible for a lot of people thinking about and rethinking how we can use the latest telescopes to find out and using these subjects. Okay, next, exoplanets. So exoplanets are smaller than neutron stars, so the cross-section sensitivity range is not going to be as good. But we do a fun few things with exoplanets we can't do with any other object. So this plot here is showing you some mock data for what could happen if we actually found dark matter was heating exoplanets. So the y-axis is showing me the temperature of planets. Each dot is a simulated exoplanet. So black is assuming that dark matter is heating the exoplanet. And the magenta triangles at the bottom are the same exoplanets, but under the assumption that dark matter does not heat them. And what you see is, as you're going in towards the center of the galaxy, there should be an uptick, depending on what type of density profile you have, in the temperature of exoplanets. And this this blue line here is showing an estimate for the sensitivity we think you'd be able to see if you have UST. And the point is, this is something that should be detectable. So if we can detect a bunch of exoplanets that seem too hot and seem to trace the potential dark matter density profile, this is a new way, first of all, that we could potentially map the galactic dark matter density, but also learn something about the clubbings of dark. So what do we have so far in terms of data? There actually is a little bit that we have, but it's not very much. It's very limited. Ideally, you want to use upcoming or recently launched TeVPA telescopes, such as JWST, Rogan or Rubin laterals to be able to do something. The limitations of this search are really just having enough acceptable candidates. So we're going to need a lot of exoplanets detecting, and we're going to want to have really the right type of candidates detected. So if we find something really young and really hot, we're not going to see the dark matter heating signal. So they're going to have to be sufficiently old and the right type of candidates that we want. So generally, we don't want something like Earth-sized. We're thinking more like Jupiter-sized, or technically something also like a brown dwarf. So in terms of the benefits, there's actually a few that we get over this over other objects. So first of all, the statistics should be large. So the estimates really are that we have, billions of stars in our galaxy, and we think that now per star there should be at least one planet. So we should have billions of these sitting there, potentially absorbing dark matter. We have to still find all of them and look at them. They're generally pretty cold, so they give good signal over background compared to some other objects. And their large radius allows us to detect them more easily than, for example, neutron stars, if you were trying to do a neutron star search close by or far away. So close by, the exposure time we would need to detect one of these is really low. And we can see them sufficiently far away to try and trace the dark matter density over there. We also can probe fairly low masses compared to, for example, rocky planets or mega-seeking stars. And of course, we get this probe the dark matter density profile. So here's an example of the sort of sensitivity that we would get with exoplanets to the dark matter scattering cross-section on the y-axis and the dark matter mass on the x-axis. So note this y-axis is the spin-dependent scattering rate. If you had spin-independent, direct detection moves further across. So you can see in the top here, this is Earth. Earth is this band I was just telling you about before. So you see Earth was really pushed up much higher in the parameter space. So depending on what candidate you use, if you use something Jupiter-like, you don't have as much reach. If you use something more like a brown dwarf, because they're about the same size but denser, you can go a little bit further. So one important thing to note with this plot is we're not really picking a dark matter model, and depending on what model we have, how these bounds look really can vary. So for example, if you have just an S-wave regular high-level WIMP and you have short-range forces, you would expect you do not get all the way to the left of these plots. So instead, you'd be sitting, you can see roughly somewhere there. Oh, good, thanks. Okay, so what do we need to find these candidates and move ahead and find potential dark matter? For neutron stars, we want to find a candidate sufficiently close by and old enough and get enough observing time to actually see these. For white dwarfs, we really need to understand the astrophysical uncertainties in clusters and have more candidates. For exoplanets, really we want a large statistical sample to overcome systematics and do a bunch of detailed studies of the atmospheric effects. I'm just going to really quickly show you some work I've been doing to understand this exoplanet search. So one really good question is, how many exoplanets do you need to see a signal that you think is statistically significant? So we want to probe this unknown dark matter density profile. How many planets do we need to actually say, with some level of confidence, we think we've extracted some information about the profile and about dark matter? And what level of precision do we really realistically need in these searches to understand if dark matter is there or not? So how many do we have to know the radii of the exoplanets, their temperatures, and their masses? We find doing some simulations. This is approximately, we think, the sensitivity we would have to the Hayward parameters. So on the y-axis, this is the gamma. So this is like how spiky the dark matter density profile is. And the x-axis is the scale radius. So really, colloquially speaking, like as squishy it is. So these colored regions, really, if it's bright, it's good. If it's dark, it's bad. So the top row is if we have 100 exoplanets with increasing uncertainties on these parameters. So 10%, 20%, 30%. And the bottom row is if we have 1,000. So if we manage to get down to, for example, 10% uncertainty in these measurements with about 1,000 exoplanets, we'll be able to probe to fairly good precision more spiky types of profiles. If you have a flat one, the search is not going to do so well. Okay, just interested to carry on a bit. We've also been doing some ongoing work with exoplanet experts, which is not me, it's from a particle theorist. So really want to understand, we've got atmospheric effects, what would you expect to see? And it really doesn't look like a black body, which will be assumed in the first paper, just to do the simplest thing. But it turns out actually you can probably have much better reach if you assume, or you actually model the atmospheres properly. So what this is showing is the different temperatures for a brown dwarf, how the spectra actually look. And so we were going to use JWST, but what you actually can see is that other telescopes, so JWST peaks or is sensitive to this region of wavelengths. So Roman and Ruma go to much shorter wavelengths, but really actually the spectrum can peak due to all these different atmospheric effects where Roman would see. And Roman has a really good field of view and should be doing surveys of the galactic center. So we should get really good exposure time and potentially be able to find out that way. So I currently have this left. I'm going to just try and flash you the main result of this setting category, which is dark matter annihilation to gamma rays and neutrinos. So for this search, the classic thing is just the sun. The sun is great, it's close by, it's huge, it's big, it's hot. We really would like to use it. So there's been too many papers on this. These are definitely not all the papers. For example, Aaron Vincent, one of our hosts here, has written a bunch of really awesome papers on this topic as well. So why is the sun good? We have lots of data. We have gamma ray data, we have neutrino data. We want to take into the sun as hot, so we don't want to do the heating. We want to just look for these standalone products. And it has a bit of a higher evaporation gas compared to some of these other objects. But it's huge, it's close, we have good data. So for the sun, the first search that was done, or the first search really that was suggested, was that you can just have dark matter annihilating neutrinos, and neutrinos should just pass through the sun and we can see them directly. So in this case, the sensitivity that we have to the parameter space, so again, scattering, dark matter mass, this was as of 2017, direct detection. It's probably by now down a little bit from this. So these shaded parts are the searches with Super K Antares and IceCube as of a few years ago. But we pointed out that if you have a case where dark matter annihilates to these long-lived particles, or just some that are sufficiently boosted, you have some sensitivity at higher masses. So depending on what final state you annihilate to, you can get a number of orders of magnitude in the dark matter space. And actually, this search was just done by IceCube, who's here. And it looks like from the preliminary results, this roughly seems to agree with projections, which is really cool. So we can start using neutrinos, these bands here. We can also use gamma rays. So for gamma rays, you just get like orders of magnitude stronger than direct detection. Again, this is the spin dependent rate. You had spin independent for actually by now, like down there, as we've all seen, it's amazing. So you want spin dependent if you want to actually see this. But there are, of course, model assumptions that have to go into the scenario. So there's some way out that, like, yeah, we get from point. So we had projections with Hugh and Lasso, and the year after we put this paper out, we teamed up with some people in the whole collaboration, particularly Mereia, and actually filled in this bound here. So dark matter annihilating to any long-lived or boosted particle can give you a lot of gamma rays, but that is then really strong constraint. Okay. All right, so I'm just about out of time. So I'm going to just go to one last plot and then summarize. So you can do the same thing with Jupiter. It's really the very short story. And Jupiter, you can get a bit more reach because it just has a colder temperature. So you see the sun balance here. Jupiter can go a little bit to the left. This is a search that I did together with my collaborators in London. So we did the Fermi data analysis and then actually set the balance. This shaded region is like the best case scenario we think that you could have. So again, depending on what model you have, you will not saturate the space. So for example, if you have a short range regular WIMP, you're sitting more somewhere kind of like in here. You won't get all the way to the left or all the way to the bottom. But we need to kind of put in a model and we find it turns out the duplicate can still be pretty good. All right, I'm going to go straight to my conclusions. Interesting things I didn't mention. There's a bunch of stuff people have been doing that aren't just these hitting searches or latent searches. You can think about things like equation of state effects on neutron stars and rotation wave signatures. Think about dark matter and really old stars. Very from the beginning of the universe, you can think about how dark matter can change the evolution of stars. You can think about how dark matter can, if it doesn't annihilate, build up so much in the cores of these objects that it causes a black hole, which can consume and destroy the object. And you can also think about the fact that if you make this black hole, it can evaporate, give you neutrinos, and give you lots of other really interesting signatures. So you should check out some of those references if you're interested there. Okay, so just it's like so much fun. I feel like to play with stuff. And there are lots of really great options and opportunities arising to discover dark matter from these objects. So both heating and neutrino gamma are exceptionally possible. That's what I discussed today. We have strong constraints already from the Earth, the Sun, and from Jupiter. And we might have new sensitivity to dark matter in the near future using exoplanets, finite square dwarfs, and neutron stars. And I think the most exciting thing I really want to emphasize again is the new technology, the new telescopes that we will have in the next coming years are going to give us a really interesting window into probing dark matter properties. And hopefully we'll find dark matter. So that's all I want to say. Thanks a lot for your attention.
Thank you very much for that very nice talk. I think we have time for questions.
For those, for those long-lived mediators that you're looking at, like, what's the range of lifetimes that we can actually see? It's now in the sun and decay outside.
Yeah. So it depends on a few things. So it's not just the lifetime that you care about, you also care about the boost. So it's the product of the boost and the lifetime. And they have to then give you a decay length that exceeds the object. So if you then want to think about for some particular model, for example, you can be looking at, like order a second, for example. But it depends on the dark matter mass, the boost and everything else like that.
And is the emission always very cold when this decays? Is it always very cold?
It is if it's boosted.
Right.
If it's not boosted, it won't be.
And that just could you look for isotropic signals, say from a few 180 year old victims?
You could. I mean, it also so you want to look for isotropic signals, even if they're very boosted. If there's enough of them in the background, I think that will still be isotropic anyway.
Here's what I'm asking: do you need some?
Not necessarily.
But
No, you don't necessarily have to. The way these analyses were set up, and looking direct. So we're assuming it's very boosted. If you don't need to have that assumption, you just have to do your analysis a little bit differently because you don't assume it's a point source.
Thanks.
Thanks for the questions.
I think there was some question you said.
Thanks for the great talk. I was gonna know for the for this calculation, is it just assuming a general density of dark matter, or have the impacts of potential wear of the local objects be taken into account? I mean, the excesses of dark matter density around the local potential level of this object.
So you're thinking like sun structure, for example?
No, for example, around the sun or Jupiter, we expect an increase in the density of the dark matter, so we should expect
Oh, okay. From like gravitational focusing?
the gravitational potential, increase in the gravitational potential level.
Great question. So we also check this. It turns out it's negligible compared to the amount that you have in position. So in terms of how much that would actually change the signal that you're seeing, it doesn't really do very much. So like from the fact that the sun, for example, if you're looking at the Earth, the fact that the sun is going to pull more dark matter in around the Earth, that doesn't really change the conclusion.
But I think that is that because like we assume like heavier dark matter particles there, or like for lighter dark matter.
This is true.
Could have a higher impact, right?
So this is true for any classes. For the sort of masses that you can probe with these objects, this is a true statement. That it doesn't really make a big difference at all. Yeah, thanks for the question.
Okay, I think we should probably move on, but first let's thank Rebecca again. Next talk is by Gopolang and Mohlabeng. It's all the microphone. So. And then we will talk about direct detection of low mass asteroid.
In theory, can everyone hear me? Right. Great. Thank you, all the people who talk and actually you organize this for inviting me back to Kingston. So I moved from Kingston exactly 1 year ago. Yeah, almost a year. So it's my first time in a long time giving a talk to so many eyes. So I'm first gonna like reduce my stress a little bit and tell you about where my name comes from. So my name is probably a very weird name that you've never seen before. So I'm from South Africa and my name is pronounced Gopolang. And in my home language of Sotho, that means remember. Usually people can't remember my name. Because it's too long, and people can't pronounce that. So I ask people to call me Gopi. So I'm going to be telling you about the direct detection of low mass dark matter today. And there are two things that you're going to be getting after this whole conference is done, which is the timeline of dark matter or the vast range of dark matter. You're going to be remembering that for the rest of your life probably, and also direct detection, the direct detection. So again, let me show you again the timeline. If this thing works. Okay. So the range of possibilities of dark matter is very vast, as you've seen from the two great talks this morning. For the past decade, we've been focusing our searches on the WIMP region of parameter space. This is because the WIMP hypothesis is very well motivated, and this was a very large search program for us to go look at it. And the current status of the dark matter direct detection we've seen again from the two talks this morning is that we have a large range of experiments that have been searching for dark matter between this roughly 1 GeV to tens of hundreds of GeV within TeV. And this we seem to be hitting a wall. This neutrino fault that Hugh explained really well this morning. And so I'm not going to go too much into detail about this. Now, this compels us actually to start looking at different regions of search. This compels us to look at different regions of search. We can look for ultra-heavy dark matter scale and go into much larger masses in the form of ultra-heavy dark matter, or we can go to even to much lower masses. And so we might ask the question in the sub-GeV range, what or who lives in this region of parameter space, and then many opportunities to explore here. We've heard some of these about some of these in the nucleus scattering regime from Marie-Cécile this morning, and some of this from the previous talk from Rebecca. And so the low mass sub-GeV searches are complementary to WIMP searches. We're not replacing WIMP searches, but we're looking at the same time parallelly in different regions. These are very well motivated because if dark matter interacts with the sun metal through some unknown force, this presents a very good target for us to probe how dark matter was produced early in the universe. There are mechanisms like the thermal freeze-out, freeze-in, and asymmetric dark matter. We briefly heard about freeze-in from Caitlin talk on okay. Unfortunately, the big stumbling block about detecting light dark matter using current direct detection experiments that are looking for WIMPs is that these are light dark matter is invisible to these experiments, and this is because these experiments are looking at KV recall thresholds, and the dark matter that we have that is much lower cannot produce sizable ripples enough to be seen in these experiments. So basically, it's like a ping pong ball hitting a bowling ball. There will be a ripple, but we're just not going to see it in those experiments. And one way to think about this is that the nuclear equal energy goes as the reduced mass squared times the velocity squared over the mass of the nucleus. And so if I have a 500 MeV particle entering the detector and hitting a xenon atom that is roughly 100 GeV, I get a 19 eV ripple. This is obviously well below the KeV nuclear ripple thresholds that have been set by current WIMP searches. And so to probe lower masses, we either need to dramatically lower the threshold from these experiments, as we heard from Marie-Cécile's talk today, or we can look at other ways to maximize the energy transfer to the target. So one way to maximize the energy transfer to the target is to, instead of dark matter hitting a nucleus, dark matter hits an electron. And so 500 MeV dark matter particle hitting an electron will form a sizable electronic equal in the detector that we can see very well that we can look for. And so current searches in this direction are large volume noble liquid detectors like xenon 1 ton and many others, as well as small scale semiconductor detectors like a sensor experiment. And so here are two plots that show the dark matter electron scattering cross section for a heavy mediator and a light mediator. It shows the different experiments. If I'm not mistaken, with the dashed lines are the projections, and the solid lines are the constraints. And on this side, as you can see, with big experiments, if we increase the size of the experiment, we can actually probe even the freezing mechanism that I mentioned about before, which is how dark matter may be produced earlier in the universe. I'm just going to take this long and do this. So a complementary way for us to search for dark matter to maximize energy transfer to the target is, instead of reducing the size of the target, instead is to make the dark matter move much faster. And I'm going to talk about how to do that in the next slide. And so here the energy transferred for a 500 MeV dark matter particle moving at roughly a fraction of the speed of light can still hit a roughly 100 GeV nucleus and produce a 50 keV recoil energy signal. And the maximum energy transfer to an electron in this case would be roughly 2 MeV. Now, this is clearly above the thresholds that have been set by direct detection and current direct detection experiments. Not only that, but it's also above the thresholds for some very large volume neutrino experiments. So this allows us to open a whole new region of space of searches for these types of dark matter. We can look for direct detection, not only in direct detection experiments, but also in large volume neutrino experiments as well. And then it's at this point you should be asking, well, hold on a second. You're telling me that dark matter needs to be moving really fast for me to do this. So if dark matter was moving at a fraction of the speed of light, does that mean that there's no more dark matter? All the dark matter is escaping outside of our galaxy? Well, we know that dark matter has to be non-relativistic to form the galactic halo. And so any accelerated dark matter that exists in our galaxy has to be a small subcomponent of the total dark matter in the halo. And there are many ways to get this accelerated dark matter. And we've heard about this for those who were in the dark matter session yesterday. A lot of great ideas that I will go over in the next few slides. So one way to do this is to look at cosmic ray accelerated dark matter, where we look at high energy cosmic rays hitting ambient dark matter that is between us and the cosmic ray. So the cosmic ray hits the dark matter, gives the dark matter a high boost. The dark matter then travels to the detector and deposits a lot of energy inside the detector. And here I'm showing the direct detection cross sections for dark matter scattering, nuclear scattering. This one of the first papers to look at this was by Chris Capielos in the audience and John Wickham, and looking at how neutrino and direct detection experiments could actually go much lower masses of dark matter nucleus scattering. So looking at experiments like IFA, Hamland, xenon 1 ton, and also these kind of infractions can also leave imprints in cosmology. And looking at various cosmological observations, we're able to set constraints on these. For the electron scattering, looking at electron scattering, can even probe much even lower masses at large volume detectors like superconducting. That is a dark matter particle that is very KeV coming in at very high energies, can deposit a lot of energy in a high threshold detector like superconducting and other neutrino experiments as well. Another boosting mechanism is neutrino upscattered dark matter, neutrino accelerated dark matter. And one example of this is looking at solar neutrinos. So we know that the sun produces a lot of neutrinos. There's dark matter between us and the sun. Solar neutrino comes out, hits a dark matter, and the dark matter travels to the Earth and scatters inside the detector. The velocity of the dark matter is directly proportional to the neutrino energy. And here this is from a paper by Hugh from Carleton. We showed that the differential flux is function of velocity. Here we see the standard halo dark matter that's moving non-relativistically in our galaxy, and this is the flux from the different types of neutrinos that are coming from the sun. And as you can see, the peak, which is about almost the speed of light. So we have this highly energetic dark matter coming in and interacting in experiments like Piro and CEvNS light, the spin dependent. Through the spin dependent interaction. Another way that we can look for this is through cosmic neutrino upscattering. And again, it's the same type of signal, but it's a different source of neutrinos. And I refer you to this talk that's given yesterday by John Gopolang. Another way to look at this is to look at all the supernovae that have ever exploded in the universe. And for the signal of this cosmic supernova neutrino background, and neutrinos coming from those supernovae can upscatter dark matter, and we look for the signal inside the detectors. And many other interesting mechanisms. I'm not going to go through all of them, but some of them here we can look for accelerated dark matter from evaporating black holes. There was a talk yesterday by Marco Chianese, sorry if I'm pronouncing that wrong. And also there's a paper that looked at neutrinos that are coming from evaporating black holes, accelerating dark matter, and we look for the signal as well. And so one direction is that a primordial black hole evaporates because of light dark matter. It can travel to the Earth and deposit energy inside the detector, or neutrino comes out, or other subatomic particles that can interact with the dark matter and can produce this type of signal as well. And there was another very interesting idea yesterday from Chris Piro, showed that accelerating dark matter can be accelerated from supernova shockwaves. So when the supernova goes off, gives off these shockwaves, and any dark matter that's around there can be accelerated as well by that shockwave. And then many others that I don't have time to mention. So today I'm going to be talking about a different mechanism of this, where I'm considering a non-minimal dark sector. And by non-minimal dark sector, I mean that the dark matter may be composed of two or more stable particles. And a generic feature of a non-minimal dark sector is that dark matter today may be composed of some relativistic or non-relativistic, semi-relativistic component. And how I can see this is by looking at different sources such as the system freeze-out mechanism, whereby I have a particle called Chi-A that is heavier than another particle called Chi-B. Chi-A annihilates into Chi-B. Chi-B naturally comes out with a boost factor that is related to the proportional to the mass ratio of the two particles. And so if there is a very big large ratio of the two particles, the Chi-B comes out at a very large boost, and I can see this in my detector. There's also semi-annihilation, in which if I have the dark matter charged under Z3 symmetry, we can look for Chi-A annihilating into a 1B and a standard model particle, which are both boosted, but what I care about most is the Chi-B particle. I can also look at decay, where Chi-B decays into Chi-A and a standard model particle here. And this is actually an interesting kind of variation of inelastic dark matter that we can look for new and cyclic signals also in collide experiments. And I think there's going to be a talk either today or tomorrow by Mateus. Who's going to talk about all these interesting signals. And so I call this scenario boosted dark matter, just to be confusing, because all these other scenarios are all boosted dark matter, but they're boosted by various mechanisms. So let's just humor me for a second, and let's just say this is boosted dark matter. Okay. And so the example that I put here is that I have a particle type A, which is larger than this other particle type B. These two particles could be stabilized by two different stabilizing mechanisms, like the U1 prime cross U1 double prime, or Z2 cross Z2 prime symmetries. And I have a generic dark matter that forms most of the dark matter in our galaxy, in the universe, and it doesn't directly interact with the standard model, but it interacts through this like a particle. Particle B then interacts with the standard model through some U1 prime interaction. In this case, it could be some vector boson interaction. Okay. And so here I can have in the center of the galaxy, or in some areas where dark matter has high density, dark matter A annihilates into B, and the dark matter in this case is annihilates through its contact operator, and the scale of lambda is set by requiring the correct relic abundance for these particles A. These come up with a boost that I mentioned before is proportional to that mass ratio. These then come at high energy inside the detector and interact through this new light mediator particle X, for instance. And there are many papers that have been written in this direction. So we can look for this, say, for instance, from the galactic center, where A annihilates into B, and the flux of this, because the galactic center is very diffuse, I can look at some angular cut, do some angular cut, and the flux that I get from that is proportional to the thermally average annihilation cross section over the mass of the particle A squared. Now this flux is actually really small, and so we need very, very huge detectors to see these type of particles. Now the advantage again is these particles coming in at very high energies, so we would be able to, they can deposit a lot of energy inside the detector, and we can look for them. And so again, I'm going to be focusing on electron scattering, but if you want look at nuclear scattering, which is a little bit more complicated for these very fast moving particles, we see this paper here by Dr. Berger. And so the boosted dark matter from the galactic center, the number of signal events is set as proportional to the flux, as I mentioned, and the differential scattering cross section of B with the electrons. And here I'm plotting the scattering cross section over mass squared as a function of the maximum energy that the boosted B particle deposits inside the detector. And that gray shaded region is we took data that was reported by Supercommunicante and set elements on this parameter space. And all these other colored lines are just projections for looking at the different neutrino experiments. So for example, Supercommunicante observing over 26 years, so double the amount of time observed for the from the black curve, gives this burgundy line. And the dashed orange and blue are due for 10 kiloton detector and 40 kiloton detectors observed over 3 years. And the green is just a projection, so super K just known up to be the size of hyper K. And then on the left, I show the mass as a function of B, of the mass A as a function of mass B, and anything that lies within those contours is what those experiments are sensitive to. And the super K, as you can see, as excluded that region. The yellow and blue shaded region are model dependent bounds coming from a non-relativistic B particle annihilating into standard model particles that then can leave an imprint on the CMB. We haven't seen anything on the CMB, so we set limits on that. And there's also a non-relativistic B particle can then enter the detector. This is actually a very old atomic limit. So this is for nuclear scattering. So this non-relativistic particle can enter the detector and cause nuclear ripples inside atomic. And we haven't seen anything. So those are the limits from that. We can also look for boosted dark matter from the sun by looking at precisely what Rebecca has talked about today, which is capture and annihilation of these particles. So these boosted dark matter, so that the A's can get captured inside the sun, thermalizing the sun and annihilating the boosted B's, which then can travel to the detector, and we can look for the capture signal as well. And to do this, we have to solve this differential equation. where C is the CC is the capture rate of this dark matter from a scattering with the nucleus inside the sun. There's a CS, which is the self-interaction captured due to self-interaction. There's CE, which is the evaporation rate. So if dark matter is that's already inside the sun, another particle comes in, hits it, it evaporates out. Once the dark matter thermalizes, the two dark matter particles can find each other, annihilate and boost the B's, and we can look for those as well. So CSE is the evaporation due to two dark matter particles interacting with each other, and one keeping up the other. And the importance of self-interaction is shown here, where show the equilibrium number density of the particles A that are accumulated inside the sun as a function of the mass of these particles. And I show that when we have no self-interaction versus when we have self-interaction, the difference is very very far. So you an increase in magnitudes in the number density once I include the minimum and maximum self-interaction. The minimum and maximum self-interaction have been set by astrophysics. So by looking at the kinematics of dwarf radial galaxies and also the matter distribution of globe cluster gives us those two numbers. So in terms of looking for boosted dark matter from the sun, for minimum self-interaction, everything that's inside those functors is what those experiments will be sensitive to. And again, we see those shaded regions as I mentioned before. And once I have maximum self-interaction, means I capture more of those A particles, they get annihilated into more B's, and the flux of B particles coming from the sun becomes much larger. Okay. So I'm not going to say more about this. Now we can also look for boosted dark matter in direct detection experiments. So for instance, the xenon one-time and dark side. And in fact, many of the models that I talked about of accelerated dark matter before were produced or were able to explain the xenon one-time excess. Unfortunately, as Hugh mentioned, that excess is gone. But we do learn something new and interesting about these models that are coming. That we can look for new and interesting signals of dark matter, all these variety of experiments. So for this, I'm going to be focusing on the electron scattering, and I'm going to explain why in a bit. And so to get the recall rates that I mentioned for the neutrino experiments, because I'm looking at such high thresholds, I need dark matter to be coming in at very high energies. And at those high energies, the dark matter essentially sees the nucleus or the electrons as almost free particles. And so in this case, looking at what goes into the signal events is the boosted dark matter flux, the cross-section scattering with the electrons, the effective number of electrons that I'm assuming inside my detector, and also the time of the exposure time. When it comes to direct detection, I have now we're lowering the threshold. You need to be looking at much lower energies of those boosted particles. And at this point, I cannot just assume that the electrons are free. They have to be bound to the nucleus. In this case, what becomes important is this differential scattering cross-section over here. This scattering cross-section is this complicated equation, but I want you to focus more on the ionization form factor at the end. And what the ionization form factor does, essentially, it takes into account the fact that the electrons in orbit have non-negligible momentum dependence, and takes into account the fact that dark matter comes in and can scatter, ionize different electrons in different shells. So non-relativistic dark matter can come in and ionize a 5p shell at most, or going to basically shells that have low binding energy. It cannot penetrate deep within the nucleus and ionize the more closer to the electrons that are closer to the nucleus. And the relativistic or semi-relativistic dark matter has enough energy to ionize deeper within the electron detection. And so the focus here is looking at calculating the ionization form factors that can take into account these interactions of these boosted dark matter particles. And so the ionization form factor is given by the bound state electron wave function and the electron wave function when the electron is free. So we need to know that, and some transition matrix elements. And what's commonly used in the literature is the plane wave ionization form factor, which assumes that the bottom state electron is in this form wave functions, and the outgoing electron is a plane wave. Alternatively, one can use a relativistic ionization form factor, which assumes nothing about the bottom state wave function or the outgoing electron wave function, but we get those wave functions by solving the relativistic direct Hamiltonian using that Hamiltonian over there. That has an effective potential term in the end. I'm almost done. It has an effective potential term in the end that takes into account the Lorentz structure of these electron interactions. And so what I showed here is the ionization function as a function of the momentum transfer, and show that at lower momentum transfer, those ionization functions are almost the same. But once we go to probe high momentum transfer distributions, I see that there's a very big difference between these ionization form factors. That tells us that if we don't take into account the relativistic ionization effects, we tend to underestimate the regular rates for these electron scattering or these electron sections. And some preliminary plots. Here I show the direct detection, the scattering cross section is a function of mass of particle A for some benchmark parameters, showing the plane wave and relativistic ionization form factors, and show that we get different results depending on the ionization form factor that we use. And you may wonder and say, but this is such a small difference. One, this is a benchmark parameters. These could change with different parameters that I choose. This model has a lot of parameters because I'm looking at a multi-component dark sector. But also, if I include the Lorentz structure here, for instance, if I look at pseudoscalar mediator, I start seeing a big difference between the plane wave and the relativistic ionization form factors in this case. So, while accelerated dark matter is very interesting, there are many boosting mechanisms. We can look for striking signals and direct detection and neutrino experiments. We need to be careful about the ionization or the atomic effects that we include in them. And well, we need to include the atomic effects. And so ongoing work here includes looking at the different experiments, both the direct detection and neutrinos, and the cosmological constraints, as well as trying to incorporate in the study all the some of the other many different boosting mechanisms that I mentioned before. That's it. Thank you.
Thank you very much, Roby, for this nice talk. I think you have some time for questions. Yeah.
So from the direct detector point of view, say OZ, is there anything we should be doing differently to enable such analyses? So
That's a good question. See, I don't really understand the like the detection prospects inside LZ yet. Maybe this is something that we can talk about.
and we should do.
Any other questions? You're wrong. The next up, was dates, 15 and 16 of the so then what happened the accessible. I was wondering, you mentioned I'm thinking about this, but when you're looking at stability from slide 16 to the next step, what do you think the guys will leave in sort of the left? And I wonder if you thought about Piro.
So I talked about Juno. No, I haven't thought about Juno. It's something to get included. The reason we haven't included Ice Cube here is because the Ice Cube threshold is way too high for the mass range that we have here. So Ice Cube would be in this parameter space, but we'll have to change the parameter range of the dark matter in order to fit the Ice Cube. But yes, the Ice Cube is very interesting for this. In fact, what we wanted to do as well at some point was to look at Pingu, but and in the end, it turns out Pingu was not going to happen.
Thanks. Any last question?
Are the ionization effects significantly different between xenon and argon?
Between xenon and argon, that's something I'm still investigating. So the point now is to look at the change, be able to transfer the recall rates into the number of ionized compounds, and then convert that into the photo electrons come from that. And trying to see whether between xenon and argon, what are the differences, and also the boosted dark matter. Do I ionize more electrons than compared to the non-relativistic compound?
Thank you.
Okay, I think we should probably move on, but thank you very much, TeVPA. And we have the final talk of this session. Not like. Try again.
Can you hear me? Okay.
So the talk is going to be a little bit tough for me because I have to fulfill the two goals. One is to give the talk on behalf of Melissa, so I'm only not Melissa. See, unfortunately, we can be here. So see, I think the to give this talk on her behalf. And the second is that I have a complicated task of smoothing out the simplificating. Sorry, I don't know what they came first. Smoothing out the transition between dark matter and light matter. Okay, so the goals of the topic are basically to convince you that the Blazars, the types of software that you can observe in very high gamma rays, are important not only because of the physics behind it, but also because we can actually cosmology and fundamental physics with them. And the glue that sticks these topics together is the study of the transmission of the universe to gamma rays, and particularly the stellar right. So let's start with what is the EVL. EVL is just a emitted light that has been emitted by different processes since the time of realization. No? So it has a two-component structure.
Might be too bright.
The laser doesn't really work.
So it has a two-component structure, one side in the optical, which we think it is basically a starlight emission plus some other processes such as APN emission, etc. And then there is a second one, which is shining in the infrared, which we think it is just reprocessed emission by a dust illumination. It has very important things behind that, such as it contains information about the organization, star formation, it traces the star formation that evolution of time, how galaxies form and evolve, and the emission by accretion processes such as Leane. So yeah, basically I told you that it was already there is the cosmic star formation history. So it's going to be important to study how the AVL evolves because it gives us an independent measure about how many stars form a long time. And it also includes some signatures, some important signatures from the ancient past, such as the reionization signature of 1 micron or this polycyclic aromatic metamorphosis carbons of 15 microns. It's also it can also contain other calculations of that emit this light, for instance, unresolved components such as the population of stars, decay, etc. And it's very relevant for cosmic ray propagation. And finally, it might even be linked to their physics. because, for instance, corporal supernova can contribute both to lineal, the optical part, and also to an diffuse supernova background of linear data. So observational is also relevant because it limits the distances that we can observe the sources like particularly in the gamma ray band. At some point, when we go to very high energies and very high distances, the universe becomes opaque for gamma rays, for photons, and we can only do astrophysics with other alternative instances of neutrinos. It also modifies the emission that we see from distant sources. For instance, here you have in the right blazars, two blazars, and how the spectrum gets modified. The lines, yeah, the intrinsic spectrum is modified by the emission from EVL, when we observe something that is completely different, each standard. But it also affects other sources, such as GREs, which can be observed at very high distances as well. So how do we measure this EVL? There are different methods that have been tried. One, the most obvious one is to try to directly measure it, but it's complicated. It's the second most intense background radiation after the CMB, but still there are a lot of foreground sources that limit the possibilities of doing this direct measurements. No? So we have to model a lot of components such as starlight emission inside the galaxy, diffuse galactic emission, and many other scattering processes, for instance, so we have light, etc. So it's really complicated. There are alternative methods that try to remove some of these foreground components, for instance, that nebula method, in which you look at two directions, one which has a dark nebula that is blocking the light in it, and another that isn't blocked. And by doing that, we can subtract everything that has been emitted in the dark nebula and us. But still, there are lots of systematic uncertainties in this. So there are other alternatives that we can try. One is through galaxy counts, just by counting the number of galaxies and interpreting the entire light that they are emitting, we can try to set strict global limits to the radial intensity. And they are quite robust in the optical, and they are even reaching the point where they are touching measurements that we can make under measurements and direct measurements. So we think with this that most of the light that comes in the optical part is just coming from normal stars, and there's not that much room for other components right now. Other possibilities that we can try are, for instance, through modeling, and models can come in different flavors. They can be more empirical, just based on the measurement of the local luminosity function, or even the evolving luminosity function with reflected. They can be more phenomenological, in which we measure the cosmic star formation rate, and then model the radiative transfer and some population synthesis models to try to recover the ABF grid. And finally, there are more analytic ways of modeling data. For instance, based on MOD simulations, and then accounting for all kinds of variance processes, dark matter clustering, feedback, galaxy formation and evolution, etc. And then finally, this will fit some observables and we get our EVL. Just to remark that EVL models are very dependent in the optical band. So there are not that many dots there, but they start to diverge as soon as we enter the unit. Okay. So that's where we need to do something about. I said that it is important because it limits the distance of what we see the gamma rays, not from distant sources. And we can actually use that in order to measure the EVL number. So for instance, when in this direct measurements of the EVL, we use distant gamma ray sources, and when these gamma ray sources they emit light, this light can interact with the photons and produce bursts of particles, typically through electrons and positons. No? It's some pressure conditions. So this absorption depends on many factors. One is basically the cosmology, and that's interesting because we can try to even invert this expression. One that depends on the EVL spectrum, and then there is the scattering and all on the interaction itself within the EVL photon and the gamma ray photon. Here you have the attenuation factor that is introduced. So this is exponential of the minus optical depth over energy for different reflets, and the same thing for the optical depth as a function of the energy and the rest. So what instruments do we use for studying the ABL if this and Lippincott? You can use either instruments on space, typically Fermilab, or instruments on Earth. Here you have the three current generation ICPs. And both provide complementary measurements because they have access to slightly different range in wavelength of the ABL spectrum. The targets are typically distant sources, and the most probably most numerous ones that we can think of are blazars. These are just AGNs in which we have a jet is pointed toward the lines every time. And that causes some amplification of the emissions that we see. So they are Doppler boosted, and that makes them really nice sources because they are very numerous and they can be observed at very high distances, which are just the two ingredients that we need for this kind of measurements. But they have some problems. First, we are not fully sure about the increased emission, and it might have internal absorption, cutoffs, because of the underlying particle acceleration processes, etc. They are also typically very variable, so that makes something interesting that if we observe a source and we integrate a lot of observations, we might be missing different stages of activity, and that makes the entire modeling of the interest absorption complicated. And finally, in some cases, the ref seed is not very well determined, and that's also because, particularly in the ones that peak at the highest energies and therefore are the most likely sources to be detected in very high energies, those usually don't have emission lines spectrum, so that makes the distance determination complicated task. The blazars have a very simple in principle spectrum. So they have basically two components in the non-thermal spectrum. One that comes from the synchrotron, that's very well known from Hubble electrons, but their high energy part is not very well known. And both tonic and hadronic emission models would explain the both have issues, some issues, for instance, explaining the variability of the sources, the magnetic fields, etc. And there might be even further components to this emission. A particular nice kind of sources in this category are extreme BLS. It is because in principle these sources are quite numerous they're becoming quite numerous in very high energies because typically the high energy component is pretty bright. On these ones, they are usually not very variable, so that means that we can stack data often. At least in those cases of the non-changing BLS. And finally, in some cases, we have a pretty hard spectra extending well into the very high energy band. So that makes a nice target for this kind of studies. But they have basically the same issues as other lasers. So we don't know about the intrinsic emission. It can be either tonic, hadronic. It might have either other component and other components, but pretty complicated the view of this structure that we have. There are a lot of ongoing efforts to try to detect more of these sources. Some of these have been presented in this meeting, and this has given a lot of new targets that have been discovered with ICPs recently in the last 2 years. That's great for the development. So once we have the targets and the instruments, what can we do about the data? So how do we get the deal out of it? So we start with an intrinsic spectrum that is absorbed by the EBL, that is summarized with that optical depth. And then we get the observed spectrum. Of course, using more physically motivated models is complicated because they have a lot of parameters, and often the data in gamma rays is not that detailed. So we have to make some simplifications, and it is usually done by assuming some very simple models to reproduce the intrinsic emission from blazars, and they have been motivated by observations over 30 years of remuneration ICTs. So typically we have a simple power law, a low parabola, power with exponential cutoffs, etc. And with this we have two possibilities. One is to jointly fit the ABL intensity plus the parameters from those simple models. And the other is just to assume the spectrum coming from instance for measurements of the lower energies, which are not absorbed by the ABL, and then trying to see how much light are we missing because of the ABL. Either way, we're making any assumptions on this. So all the major gamma ray instruments have provided already measurements of the ABL, starting from Fermilab. In this work, they consider a large set of lasers, more than 700, with a wide range of reflection. And what they could do was to, because they had a great signal, they could even not only estimate the radial intensity, but how it has evolved over time. And remember that that's linked to the star formation history. So they made an estimation of the star formation rate and how it evolves over time. And those measurements, this one here, is really comparable with other measurements done with completely independent methods. And even it signals the peak of this star formation history. So that's really nice. And it has, well, these results have been even extended to very high reflection, including other sources such as the areas. Regarding ILCTs, one of the first works that was done was with using archival data taken over 30 years by this work on Williams. They took all this spectra from many blazars, including 15 extreme blazars, and well, over 80 spectra. And what they did was a wavelength result measurement of ABL. This has been improved recently by the design, who updated the Fermilab data set and used the same ICT data from Piro and Williams and got compatible measurements with some small differences that in the ultraviolet path. Okay. Then carbon generation ACDs have all performed measurements that are similar in Lippincott because they are using a collection of sources with hundreds of hours of data and quite wide range of reflection. And basically, what you have to take from this slide is that the selection of the sources and the selection of the data is completely independent. So they are complementary in a way. And they would even combine the feature. Starting with tests, they made an assumption for the intensity spectrum just using a loss parabola. They did the intensity of the ABL. With that, they could resolve the ABL pretty well in the optical rates. No? The magic, they did something a little bit different. So instead of just doing this search over different wavelengths or even beams, they did that to approach system. No? So the first one was completely independent. So they were just scanning one EVL model, and with that they had enough significance to do a search over reflection of the evolution of the EVL, and then another search independent, which is wavelength result. No? So they forget about this. They just focus on the local universe, and they did that wavelength result. And this is the result. So they are scaling an EVL model, but just in pieces of wavelength, so that the dependency on the model is kind of broken. And they saw some excess here in the ultraviolet, but they did the profound system analysis not that significant. But it is interesting to see how far it gets in wavelength of the constraint and how it matches the levels, no, and the galaxy comes. Finally, Veritas they did something completely different. Instead of just focusing on specific EVL models, they did as a grid search over this parameter space of intensity plus wavelength. So they generated 500,000 possible EVL6, and they just feed all of those with the data they had and weighted them in order to get an EVL. This is the results they got, and it's significant how constrained it is in the upper one. The lower one, we don't care that much because we have already the galaxy rounds, and those are pretty constrained in the results. So this is the result. Is the EVL result. It is in the optical part. So we have a good handle on the intensity of the ideal in that part. And the only dots are the infrared part, the evolution with reset, and finally the infrared component, no? In which all the models live in the part, and also the measurements are pretty cool. So how do we access that infrared part? One idea is to use very nearby sources. They need to be hard, they need to reach pretty high energies in the detection. And one possibility is to use, for instance, radiographies. Sources such as NFP7 in principle are ideal for that. They are super close, 0.004, and they are proving directly the EDR intensity of 30 microns over. So there is an ongoing effort by the three analysts to try to handle this source intensely, and that's flared coming from. Another way of studying the EDL that is worth to mention is that this is starting to pop up now with the detection of the first gamma ray burst. Some of them are pretty high frequency. Okay, so what can we do with the EDL measurements? I said that there were basically two things that we could do. One is cosmology, the other is fundamental physics. So let's start with the cosmology. I said that the optical depth depends on these factors, and we can try to invert them. Let's say invert, but even this one generalized like the no. So instead of just focusing on the density of the EDL, we can try even to search over cosmological parameters such as the Hubble constant or even the matter density in the universe. No? This is done by Leane Williams with this set of gamma ray data, and they got constraints on Hubble constant that are complementary to other estimations using, for instance, methods such as the distant bladder or the CMB. No? This is completely independent. And this has been improved recently by Alberto Dominguez, who did a search not only over the Hubble constant, but also on the matter density. They got pretty loose constraints, but it's starting to be possible to do this kind of searches with these data sets. So the other part is to try to do fundamental physics. And that's where the other part where I want to talk a little bit about dark matter. So in some theories beyond the standard model, these action-like particles pop out, and they are dark matter candidates, and they can travel with photons under very strong magnetic fields. No? A photon is traveling from a distant place, whereas can turn into an action-like particle, travel unaffected by the EDL, so unabsorbed. And then in the local universe, if it encounters a kind of strong magnetic field, it can turn it back into a photon, and we can detect that. The effect is that the opacity of the universe gets modified, and we no longer have this super strong cutoff, but we have some recovery with the gamma ray signal. And by measuring these kind of wiggles, the spectra, the spherical spectra, we can try to set to do measurements of these particles. Unfortunately, the data we have is telling us that we cannot constrain this as well. I mean, there are some limits, but everything is compatible with just And the final thing is Lorentz invariance violation. No? Lorentz invariance violations appear when we try to couple quantum mechanics with gravity. And in this case, what happens is that the dispersion relation gets modified by a factor, and linear, quadratic, subluminical, superluminical, etc. No? So different flavors we have. And people have made predictions on how the opacity of the universe gets modified by this phenomenon. And it's interesting to know that the constraints we get using this method, and the method on the leaves, on the Lorentz invariance violation, are compatible, let's say, competitive with other methods, for instance, based on time delays, Blazars, for instance, or photon decay. So with this, I get to my conclusions. I hope I have convinced you that these Blazars are interesting for doing this kind of studies of fundamental physics and cosmology. The measurements that we have are consistent with the lower limits from the galaxy counts. So everything is consistent. It's just emission from normal stars and galaxies. Measurements are growing in power, so they are becoming less sensitive to, for instance, the knowledge of the intrinsic spectra from Blazars. COB is well resolved, but CIV not. So we need to focus on that part of the radial spectrum. Finally, just to remark that extreme lasers are particularly interesting in their research as of now.
Thank you very much, Mereia. We have some questions.
No, okay,
We have some simple questions.
I don't know my question. The Hubble constant stuff was doing use. Are you calibrating standard channel or is this, how does this work? I didn't entirely follow it.
Okay, so I mean, you can decompose that term. I'm not sure if this would explain.
Powerful.
I don't think so. No. Well, I mean, go back. Okay, so this distance element can be decomposed in an expression that depends on the Hubble constant. So by doing this searches over the optical depth radially, and then assuming models, we can do this search where in the end over the parameters.
Are they still using signal?
I mean, but it's super hard completely independent of this.
Okay, that's my question.
But this requires you to assume some model of so that you have to assume number. Okay. Do you have any other questions? Sorry, I have a question about, so you're looking at this from the perspective of measuring or extracting the EL from these Blazars. Does this mean it's very hard to actually work out the intrinsic spectra of Blazars because of this uncertainty on the EL?
I mean, it's hard because we don't have access to the intrinsic spectrum. I mean, you can look to close by sources that are supposed to be not absorbed, but it's hard to start conclusions because every source is different. Some sources have internal paths in the spectrum, internal absorption because they have more components in the laser structure. While some others are more simple, and we don't see the paths. It's complicated to make assumptions.
Okay. I think we can stop there. Let's thank Mereia right there.